We're doing Net Plus. We are here in 125. Module 4 is basically the Network Plus certification. So this is very familiar ground to me and hopefully to you. It's pretty much a rapid review of Net Plus. So let's do some of this, which is here. The CISSP is pretty much Net Plus and Security Plus and about one more certification worth of additional information. All right, so network architecture and design. A simplex network is one that only goes one way. Like broadcast television, it's only transmit, not receive at all. Half duplex, you can send or receive, but you can't do them both at the same time. So this is the old walkie-talkies where you talk and you say over and then let up on the button to listen. And most everything now is full duplex, like a modern telephone where you can talk and listen at the same time. So it's just like talking with somebody physically in the room where everybody can all talk at the same time. Baseband is when you have a transmission medium like a cable and all the bandwidth of that cable is dedicated to one signal. This is what Ethernet does. Only one transmission channel is going down the cable. It's full duplex, but only one sender and one receiver is being used here, although you can have trunk lines that mix them together with packet switching, but the point is it's all dedicated to one channel. Broadband is something like broadcast FM, where you have a certain bandwidth from one frequency to another allocated to one transmission, and other bandwidths are used for other transmissions, so your bandwidth is limited, and many different signals can share the same transmission line. Analog is the old-fashioned way, where you have a vibrating, usually electromagnetic signal, and it is just fed into a speaker at the other end, so it is not digital or discrete. It's just created by picking up something with an analog microphone, sending it down an electric signal and repeating it at the other end, and therefore it degrades due to attenuation and noise, and there's no way to fix it. Digital signals digitize the signal when it's measured, turn it into numbers, and transmit it as discrete pulses of zeros and ones, and the advantage of this is you can reconstruct it at the other end and then calculate a checksum to see if blocks of data are correct and retransmit the blocks of data that are damaged so you can get a perfect copy at the other end this way. So that's why digital signals have pretty much taken over everywhere, because they can achieve essentially perfect transmission, and analog can never do that. Every transmission degrades the signal. Local area networks are within a building or neighboring buildings. You got metropolitan area networks, and wide area networks is something big like the internet. And a personal area network, the main ones you see are LAN within usually Ethernet range, 100 yards, WAN, wide area covering cities or across nations, and PAN, the personal area network, all the devices you carry on your body, like your earphones and your cell phone and the things that are connected typically by Bluetooth. So the internet is the global collection of all the networks running TCP/IP. You can have an intranet, which is a privately owned network, not available to the whole internet, which is what most companies have. They have some private servers that you can only get into by logging in through something like a VPN concentrator to prove that you're actually a company employee. They don't let the random people on the internet into there. And you can have an extranet that connects private internets, which is very common, that you have business partners and you give them some access to your network. And this is, of course, a risk. And a lot of companies like Target get hacked through those business partners. I think Target got hacked through the heating, ventilation, and air conditioning company. And BART data got stolen by one of the vendors that sold BART tickets. You know, it's a problem when you connect to another company. Now some part of your security can be compromised through that other company. Circuit switch networks is the really old system where they would have all these telephone operators wearing headsets plugging cables in, so a mechanical connection would give you a unique set of wires to make a phone call. Nowadays, you use a packet switch network where the data is broken up into packets, and the packets travel like cars on a freeway and are reassembled at the other end, so many different transmissions can share the same line. Quality of service is available in modern networks, so you can label a packet with how important it is, and it is possible for those packets to get priority, which is important because voice communications can only put up with maybe 10 or 20 milliseconds of delay before it irritates people, whereas things like email and web pages can take a few seconds of delay and it wouldn't matter. Do we know how Oakland got hacked? I haven't seen any technical details. I know it was ransomware, but exactly how it got in, I haven't seen a statement. All right, so now you have layered design. This is really important. For example, consider your power. You have these three-prong power outlets in the wall, and you buy all these devices, and they all plug into the same wall. So they all have exactly the same plug, and they all accept exactly the same voltage. This is what you need. You need to have standards, and now you can have two separate activities. You can have a power supply company making the power, and separate companies making the devices, and they can interoperate as long as they obey the standards. And in networking, you have two models to define these standards, the OSI model and the TCP/IP model, so your networking devices can have a narrow range of functionality to just do part of the job and interoperate with devices or software at other layers. This is really important. When I first started in computing in the 79 and 80, the computer at that time, you had to buy a computer and you had to buy a special printer to go with your computer, and you had to buy special software that could print on that printer. And if you wanted to print on a different printer, you had to change the software or the computer. There was no interoperability because it was not broken up into layers the way it is now. So you have a network stack that does this. The OSI model is the international one, made in Europe. The OSI model is the most common one people talk about, but it's not really real. The bottom 4 layers are real and really matter. The top 3 layers are pretty much all smashed together in practice and just built into your browser, and the difference between them is sort of arbitrary and theoretical and doesn't really matter much in practice. But the bottom 4 layers are very real and very important. And so here's the mnemonics for it. Please do not throw sausage pizza away, or all people seem to need data processing. You need to know these layers by number and order. They're very commonly used to explain networking protocols and devices. So layer 1 is the physical connection between devices, typically with a cable, although you can do it wirelessly. So let's move bits. So you have fiber optic or Ethernet cables or radio waves, and a bunch of devices at this level, hubs, repeaters, and cables, are all just physical connections from one device to another. Layer 2 is where you have frames and MAC addresses. So now you have the first layer of addressing. The MAC address is a sort of random number that determines a device on an Ethernet network, and you can aim traffic from one device to another by address. And this is what your Ethernet cards do. And switches and bridges are the networking devices that connect Ethernet cables together. You can connect them with hubs. And hubs are stupid layer 1 devices that move the signal without understanding it. But switches and bridges do read the address and only forward the signal to the correct location. So the data link technically has 2 sublayers, media access control and logical link control, the lower half and higher half of it. Then the network layer is, now Ethernet is only used within a local area network up to 100 yards. So you can't use a MAC address to really send data very far. You only use it to send data on your local area network. If you want to move any distance, like from your computer up to a server like Google, you have to go to IP. IP is what moves the large distances from one building to another or one nation to another. There's 2 versions, the older IP version 4 and the new IP version 6. And you put your data in packets, and it then routes, bouncing off a whole series of routers to move across the internet to find the target, which can be anywhere in the world. Then above that, once you've found the server you're going to, the transport layer is what reconstructs the data that may be in many packets. So you have segments here, you have UDP or TCP, typically protocols for this, and TCP is reliable. So it puts a sequence number on the segments, it verifies that they've been received correctly and retransmits them if they've not been received, and then they can be reordered. So you can do something like download an image, and you'll get all these TCP segments, and your computer will reassemble them to reconstruct the entire file. UDP doesn't do any of that. It just makes best effort delivery one by one, and if they get there out of order, it doesn't matter. If some of them are lost, it doesn't fix them. So it's useful for things like a real-time security camera, but it's not useful for moving files, like images and email. The session layer is where you have something, for example, where you have to log in. So it's not just a matter of getting a connection from one computer to another. You have to do something else that records that now I have a session, for example, for a file share. And then presentation handles organizing the data to make it more useful, for example, resolving character encoding and encryption and compression to reorganize the data to be more useful to the application layer, which is what presents it to the human. And that's why I say your browser typically does everything above layer 4. It takes the data from the segments and handles it and lets you see it in a way the humans can read it. Someone has a question. Is the firewall setting more complex when the private IP of IPv4 turned into public IP? Yes. This is a very good question, Shu. It is actually a huge bone of contention in the world of IP version 6. In IP version 4, most people use network address translation, so you have private addresses and you have to translate them to public addresses. In IP version 6, you are not supposed to do that, although a lot of people do. And therefore, every device technically has a public address directly connectable from the internet, and you have to filter the packets at the firewall. Technically, you can achieve the same security you would with private addressing, but in practice, many people are uncomfortable about that, and they use network address translation even in IP version 6. This is a big argument in the IP version 6 community. And IP version 6 tunneled inside IP version 4 has been popular for quite a while as just a way to get a temporary software version of IP version 6. It's not that common anymore. Many people now have IPv6 native networks. We seem to hear Comcast customers have had native IP version 6 for about 6 years. A lot of us are using IP version 6 without even knowing it. But there was a period when there was a lot of transition technologies that would carry IPv6 over IPv4 and so on. These are very good questions. Let's try a Kahoot. 4A, somewhere in this mess. Okay. Yeah, I taught a bunch of IPv6 certification classes years ago. Went through all those tunneling technologies, but people lost interest, and I quit teaching it. But there are a lot of complicated ways to do it. But mostly, everybody has native IPv6, and it's not that hard anymore. There was a really fun hurricane electric certification. I don't know if it's still up, but it was a hands-on certification where you'd have to demonstrate, you had to set up a server and achieve all these different levels of correct IPv6 handling, which was really very interesting. What's the overhead for doing that? Well, it's not that much. Putting IPv6 inside an IPv4 is not that much different than, say, a VPN. It's a packet inside another packet, but there's a lot of protocols that put a packet inside another packet, and it's really not that much overhead. Technically, a little bit of more processor time and a little bit of extra data in each packet is used, but not that much. Give it a few more seconds. Aha, as I thought, somebody's coming. Dot. Someone terse. All right. All right, so what kind of transmission goes through Ethernet? Oh my. So now this one's set to a minute, which is silly. Anyway. Doesn't matter if people answer sooner. Baseband among these choices, where all the bandwidth is used for one transmission. I see a question. Is there a Python book specifically for cybersecurity? There are ones specifically for attack, like Gray Hat Python and Black Hat Python, specifically about using it for attacks. That's as close as I know to that. I read Gray Hat Hacking and found it very difficult to understand. Didn't really like it too much, but some people like it. All right, what OSI layer uses MAC addresses? All right, layer 2, good. All right, yeah. All right, what layer has hubs? Yep, layer 1. Simple, unintelligent, direct connection. Does not read any addresses at all. All right, what layer has network file shares? Yep, technically layer 5. So 4 and higher is the right answer here. All right, TOH, I think we know who that is. And who Rouhani is. And very good. All right. So, the TCP/IP model is the international model. A wire network file share layer 5 because you have to log in to prove that you're authorized to reach the share. That's typically why you'd think of it as layer 5. But in fact, up in 5, 6, and 7, things often get kind of fuzzy. And all right, let me make a note of who Tao is. All right. Anyway, so this is, like I say, these 3 are really just one thing. So in the TCP/IP model, they don't bother to separate them. They just call it the application layer, which is the way it really is, and then transport internet. And they also merge these 2 together to call them network access. So this is a simpler model, which is probably closer to the way real hardware and software is. This is a little more detailed, but a little bit separated from reality. All right, so that's the game here. Then the network access layer for MAC addresses, the internet layers for IP addresses, and the transport layer for TCP and UDP transport protocols. And above that, the application layer, which is everything that will eventually take that stuff and present it to the human user. Now, encapsulation is what's going on here. Every layer takes the data from the previous layer and encapsulates it and adds an address to it and puts it back up. So at layer 4, if you think about sending an email, you press send in some kind of email client, and then at layer 4, it breaks it into segments and attaches a TCP port to it. Then that's encapsulated in a layer 3 IP packet that will be transported physically to the right device over the internet. And then that's in a layer 2 frame that will move it to the right device on the local area network. And then that goes over the wire, and layer 1 is bits. So many layers of encapsulation. It's like you have a box, and inside the box is a smaller box, and inside that is an envelope. There are layers with addresses on them. So the segment is the layer 4 unit of data transfer. Layer 3 is packets. Layer 2 is frames. And layer 1 is bits. These are the correct terms for the units of data at the different layers. So they call it decapsulation at the other end. So when you hit send on an email, it goes down through the layers and gets sent out as bits down your wire, and it gets eventually received at the other end as bits, which are then converted into frames, and then converted into packets, converted into segments, and the segments are rearranged to create the application data. So that's how it works. You go down into bits, send over the bits, and then reconstruct it at the other end, going through the layers backwards. All right. So MAC addresses are unique hardware addresses. Every single NIC is supposed to have a unique address, although there are various ways mistakes are made sometimes. You have 48 bits. The first 24 determine the organization that made the NIC, and the remaining 24 are intended to give them an ability to put a unique address on every NIC. In IP version 6, they generate part of the IP version 6 address from the MAC address, which seemed like a good idea at one time and was later determined to be a privacy risk, and almost nobody uses that system anymore. IP version 4 has 32-bit addresses, which unfortunately are written as 4 base 10 numbers, which causes everybody to have to learn to convert base 10 to base 2 to understand them, which is one of the difficult things most students struggle with. And so you have these 4 numbers separated by dots. Each one can only go from 0 to 255, so each one of these is 8 bits. You have 4 of them, so the whole address is 32 bits long, which is another problem. That means there are a total of 4 billion possible addresses, and that seemed like a lot when this system was designed in like the 1980s, but it's not enough now, as a lot more than 4 billion devices are connected to the internet. So we had to have the bigger system of IP version 6 to have more addresses. So the IP version 4, at the IP layer, it has a whole series of data in the header, what version, which is either 4 or 6. Other things here like time to live, which is how many hops this can make through routers before it will just be thrown away, because it's possible for routers to get confused and send a packet around and around in a loop forever. And so after a certain amount of time, it will just be thrown away to prevent that. And then you have the source and destination address and a few other things here. There's this awful thing called fragmentation. You see a fragment offset here. It is possible. There was a time when there was a very old protocol called token ring that could move something like 10 kilobytes in one packet. And then there was IP that could only move 1.5 kilobytes in a packet. So it was possible that you would have a device that received one packet and the output could not take a packet that big. So there was this thing called fragmentation, where you would take one packet and cut it up into multiple fragmented packets to move it along. This turned out to be a usability problem and a security problem, and was not retained in IP version 6, but that's called IPv4 fragmentation, and there's a hacking tool called Frag Router in Kali and other hacking distributions you can use to fragment your traffic, just so it's very hard for network intrusion detection systems to detect an attack, because they only see a little bit of the data at any time. Anyway, in IP version 6, they use something called maximum transfer unit discovery. You can do it in IPv4 too, where you send packets to find out what the maximum transferable unit is, but it's all pretty much obsolete now because everybody pretty much uses IP, and the packet size is about 1,500 bytes. But anyway, yeah, that's right. All right, anyway, IPv6 simplified the header. There's much bigger source addresses and destination addresses. There are 128 bits instead of 32 bits, but most of the complicated stuff has been removed. There's not very much left here at all, except a flow label, which is used for flow routing, which is a much more efficient form of routing, but it's not that common yet. So you have, if you take a Mac and look at the addresses, you'll see an INET 6 address and an INET address. This is the IP version 4 address. This is the IP version 6 address. Every adapter will automatically configure an FE80 local address. That's like 127.0.0.1. It doesn't mean you can get anywhere. It's an auto-configured address. If you have real connection to an IP version 6 internet, then you'll have a real IP version 6 net, and I believe City College now does. If I do ifconfig en0, the network I'm using now, nope, I just have an FE80 in here. Okay, sometimes I see a real IP version 6 address, but I guess not here. I think I've got it at home because I have Comcast, but the college doesn't seem to have real IP version 6 addresses. A real address would start with something like 2600. All right, anyway. So in IP version 6, the left 64 bits, which is 4 of these things, are used to determine the network, and the right 4 packets are used to determine the device. The double colon means you have a bunch of zeros skipped, so the first 64 bits are FE80, 000, and all the rest of this is the link local address, the specific identifier of this computer. Anyway, the public addresses start with 2 or 3, not F. All right, so one problem with a lot of modern networking is they have IP version 6 by default, but they don't understand it, and so they haven't put on firewalls and intrusion detection systems. The EN0 is just the name of the wireless network adapter on a Mac computer, that's all. I have a lot of other adapters. That's just how I looked at only one adapter. All right. And so there was a time when a lot of people would sneak forbidden things in networks over IP version 6. I don't know how common this is anymore, but a few years ago, it was a pretty common security flaw. You can disable IP version 6. You can just go into Windows adapter settings, for example, and turn it off. And if you do have it, if you're not using it, you should disable it so that people can't accidentally use it for unauthorized traffic. All right. Now, the original internet, up until 1993, had, well, the original one, back in the 80s, had only one subnet. The first byte determined the network, and the rest determined the host. And it would only go to a maximum of about 100 networks, because they thought that would be enough. Then, in 1993, they moved to classical networks, like what you see here. I don't know how to disable IP version 6 on a Mac. It's a good question. There probably is some way, but I don't think it's that simple. anyway, so this is the old system. It's not in use anymore, but you have to know it to understand networking because many devices still use this way of thinking. So the first half of the addresses are Class A, half of what's left is Class B, half of what's left is Class C, and Class D and E are for special purposes, and you'll never see them on an end device like a laptop or a phone. And so the Class A, the first 8 bits are used to determine the network, so each network has 16 million addresses because they have 3 more bytes to vary, and 2 to the 256 cubed is 16 million. You have 3 bytes to vary. Class B, you have 2 bytes to determine the network and 2 bytes to determine the host, so there's many more networks, but the networks can only go up to 65,000 devices. And Class C is the cheapest and most common, where you have 3 bytes to determine the network and 1 byte to determine the host, so you can only have about 250 hosts. And you can split them in between now. This is CIDR, Classless Interdomain Routing. You don't have to have A, B, and C. You can have what City College Wireless Network has, for example, is a /20, which is 16 Class Cs merged to make a bigger network with about 2,000 devices on it. You can split it so any number of bits are used to determine the network, and all the remaining bits are used to number the devices on the network. So we bring back that, now I'm on the City College network, EN0. Let's take a look. And yes, this is a subnet. What they've done here is my internet address, 172.17.21.172, and here's the net max in hexadecimal. So the first byte is 255 of FF, the next byte is 255, and the next byte is F0, 240. So this is 4, 8, 16, 20, 24, 4, 8, 16, 4, 8, 12, 16, 20 bits. The first 20 bits are used to determine the network, and there are 12 bits available to label the devices, so you can have up to 2,000 devices with public addresses on our wireless network. All right, that's an example of classless interdomain routing, where you've gone between the A and the B. All right, and then there are private address ranges. That's what most people actually use now. They use private addresses, and that's what we're using here. You saw that was 172.17. Anything starting with 10 is a private address, 172.16 to 172.31, anything starting 192, 168, and there are a couple of others. These are addresses specifically just for private use. You have to translate them into public address to get on the internet. You can neither send nor receive any traffic on the internet with these addresses. You can only use them in a private network. All right, so let's try another Kahoot. By the way, a student asked if it's possible to disable IPv6 on a Mac, and it is. You just go into Network Properties and Advanced, and you'll see here you can control IPv4 and IPv6. So I guess you could limit it that way pretty easily. Rather similar to the way you do it on a PC. You don't think you can turn it off entirely, but you could set it to link local only, which I think would almost do it. And you probably could set it to manual. It didn't look like there was an off setting though, but you certainly can control it to some extent there. All right. I think we got everybody. All right. All right, so what OSI layer has segments? That's layer 4. TCP segments. All right, which addresses are 32 bits long? IP version 4, 32 bits. All right, what class is that address in? That's class C. The larger numbers in the first byte give you class C. All right, which addresses are 48 bits long? MAC addresses used for Ethernet. All right. And you're counting again, good. Unbelievable, all right? Okay. All right, so network address translation, I mentioned before, you can technically have network address translation without port address translation, where if you have 10 devices, you have to have 10 public addresses, but almost nobody does that. The main reason they do it is so you can pay for one internet connection and share it among many devices. So you do this, you have one device going to the internet which has two network adapters, one with a public address, like this one, 147.144, and a private address, 192.168.1.1. This is typically combined with the hub, it's your router. You have a switch in one box, and then it allocates private addresses to all these devices, and they're all sharing one public address. So if each of these devices opens a web browser or something, they get translated to coming from the same public address with a different port number, and the NAT device sorts out the traffic. So when data comes in on a port number, it looks up and tells what local address and port to send it to. So it requires translating both the address and the port of the traffic. And this is what we're all using practically everywhere. Address resolution protocol is used to find MAC addresses. This is a problem. If you have a computer, it will have the address of the gateway. Like these will have an address of the gateway, 192.168.1.1, which is fine, but you cannot send any traffic with IP. You have to send it with Ethernet. And Ethernet, you have to direct it by a MAC address. So when you boot up this machine, it has to find the router to get out. And so it sends an ARP packet, which is a broadcast to every device it can reach, saying who has 192.168.1.1. And the ARP reply will tell it the MAC address of the router, and then further traffic trying to leave the network can go directly to the router without going to other devices. The problem with this is, like most fundamental networking protocols, it was designed decades ago before anybody thought about security, so this happens with no encryption, no authentication, and it's possible to spoof the ARP packets. There's also something called reverse ARP that was used to deliver IP addresses, but pretty much was replaced by DHCP. So, if you want to find the gateway, you say who has this address, and the ARP reply tells it the MAC address. So now you can find it. The problem is, an ARP poisoning is an attacker who listens for those replies and just spews back an answer, or just constantly spews back that answer all the time, and then devices will just believe that, so they will now send their internet traffic to the attacker instead of to the gateway. And this puts you in what's called a privileged position, where you're in the middle, able to intercept and possibly alter traffic. It's not that big a problem if all your traffic is encrypted, say by HTTPS, which it mostly is these days, because even though an attacker can put themselves in the middle, they can't open or modify those packets because it's all encrypted. But unencrypted traffic, it's a real problem. Unicast is one sender to one receiver. This is how almost everything's done on the internet. You can have one sender to many receivers, but the only thing that does this commonly is routers in a network. The routers send routing information to other routers this way. It's not used significantly on the internet. So this is, however, used all the time, as I mentioned, by ARP, broadcast to every device on the land. You can send it to the IP address of 255.255.255.255 to reach every device you can reach over layer 3, or you can send it to this MAC address to reach every device you can reach over layer 2, which is what devices do when they first boot up to find the router and get an address and such. There was once a time when you could send directed broadcast over the internet, where you put the network address of a place like City College and then have 255.255 here. This was used for the Smurf attack, an early denial of service attack, so now it's blocked and not used anymore. There is broadcast on IP version 6. There is a thing called multicast to all nodes, FF02::1. So technically they call it multicast to all nodes, but for all practical purposes, it's still broadcast. And it's used for routers to get addresses. All right, so if normal network card will listen to the incoming frames, and it will check to see that it's coming into the right MAC address, and if it's not coming into the right MAC address, and it's not a broadcast packet, it will throw it away and not pass it up to the higher levels. But you can turn your network card into promiscuous mode, and then it will pass all the traffic to the higher levels, even if it's not addressed to you. And this is something you would do to diagnose a problem, or because you're an attacker trying to read traffic that really isn't intended for you. So that's called promiscuous mode, and it's therefore requires root privileges, and Microsoft has various tricks to detect devices using promiscuous mode because it's considered a security risk. Nobody in your network should normally be using promiscuous mode. Then there's TCP at layer 4 with this header with a lot of things in it. The main thing it has is port numbers. You have 16 bits for a source and 16 bits for destination ports. You can have 65,000 different port numbers, and now you can have multiple services served by the same IP address. So your same server can serve email and web pages and voice over IP and other things by just serving them on different ports. So even though all those requests come to the same IP address, they have different port numbers on them, so they're sent to different processes on the server. And you have a sequence and acknowledgement number, which are used to label the packets so they can be reassembled in order. And you have these flags, which are used to send status information, most importantly, the TCP handshake. So the first 1024 ports are called well-known ports, and they're used for really important services like HTTP and FTP. The rest are, in practice, just used randomly by anybody that wants to use them, and most commonly as the sending side from a browser, which is just a temporary port number only used for one session and then discarded. A socket is the combination of these numbers. You have a client IP address and their ephemeral port, and then you have a server address and their well-known port, most commonly. So here's a client with a high local port number connecting to a SSH server at the other end, and these four numbers are called a socket, which means this device can now send and receive traffic to that device, and the two of them will have the traffic sorted so that it's as if they had a cable connecting this client to that server. It does not necessarily have any encryption, but it is a connection between these two devices that you can send both ways. All right, now there are states for the TCP socket. It can be in a listening state where it's waiting to deliver service to a client. It can be established, which means you completed the handshake. And so the handshake uses these flags. Urgent, as you see a lot, it doesn't matter that much. The main flags you care about are SYN and ACK, and then reset. Those are the main ones you see most often. There are some new flags here. So the TCP handshake, if you want to connect to a server, you send a SYN, the server sends a SYN-ACK, and you send an ACK. That's the three-way handshake. All three of those things have to happen before you can have a socket, which enables you to do two-way communication. If this doesn't complete, then you never can send data or receive data. UDP doesn't have any handshake. It doesn't do any of that. It just sends the data. You don't even know whether it got there. Mostly it does get there, but you don't know that. There's no retransmission, no reordering of segments. Therefore, the header is just very simple. There's almost nothing to it at all. So therefore, it's a little bit faster, but it is technically not reliable. in the sense that nothing is perfectly reliable, but TCP is essentially perfect because it detects errors and retransmits. So if you let it finish the job, it will get the data there. UDP does not do anything like that. It just makes a best effort delivery, and you have no reason to believe it all got there. Although, on most modern networks, the network loss is less than 1%. So mostly everything gets there, but it's not guaranteed the way it is with TCP. Popcorn? What are they?
French fries.
French fries. Oh, okay. All right. Well, I guess we got everybody that's coming. All right. So what transmission uses that address? Yep, that's broadcast. It'll go to every device you can reach on your IP network. All right, what ports require administrative privileges? Yeah, the first 1024. Those are the ones that are the well-known ports for really important services, and you have to use administrative privileges to listen on them. All right, what flag initiates a connection in TCP? SYN, short for synchronize. All right, and what flag initiates a connection in UDP? Yep, can't fool you guys. There's no connection, no handshake in UDP. You just send things to an address. All right. All right, that's Ahoy, which I guess they don't care about their points, or else they have to tell me who they are. Rouhani, I know who that is. And Billy, I know who that is. All right. All right, well, it's 5 minutes to. Let's take a break until 7:05, and then we'll do some more of this.